We hear all the time about how AI can write code from scratch. It's pretty incredible. But what about fixing code? I'm not talking about simple scripts, but those messy, complicated bugs that are buried deep inside huge real-world software projects. Now that is a whole different ballgame. And frankly, it's where most AIs just hit a brick wall. So let's just get right into it. The big question is this. Can an AI agent actually dive into a massive GitHub repository, read a bug report written by a person, and then submit a working fix? I mean, it's one thing to generate a simple function in isolation. It's something else entirely to navigate a million lines of code just to patch one tiny elusive bug. That's the real test. And yeah, for the most part, they fail. The complexity is just off the charts. To even measure this, researchers use a benchmark called SW Bench. You should think of it as the Olympics for AI software engineers. Seriously, it uses thousands of actual issues from popular Python projects, and it is brutally difficult. But what if the issue isn't just about building a smarter AI? What if it's about giving the AI a better strategy? Well, that's the whole idea behind a new system from Stanford University, and it's called CodeMonkeys. Okay, so what exactly is CodeMonkeys? It's a system designed from the ground up for this one specific task, and its secret sauce is something they call test time compute. Now that just means it's not about how smart the AI is right out of the box, but about how effectively it uses its processing power, its thinking time, if you will, to actually figure out a solution. So the system uses two main strategies to scale this thinking time. And you can think of it like this. On one hand, you've got serial compute. That's like having one genius expert who just sits there for hours iterating and perfecting a single solution. On the other hand, you have parallel compute, which is more like having a team of 10 experts all trying completely different approaches at the exact same time. CodeMonkeys, well, it does both. All right, let's get into the nitty-gritty here. The entire process really boils down to this super logical three-step method. And if you can grasp this, you'll see exactly why this system is so darn effective. Okay, now this diagram right here is our roadmap. It shows the whole flow from left to right. We start with a bunch of problems from that tough SWE bench. The first stage is context. This is where it has to find the right files to even look at. And you can see it successfully finds what it needs 92.6% of the time. Pretty good. Then it moves to generation, where it tries to create a fix. And look at this. It actually generates at least one correct fix for 69.8% of the problems. That's its raw potential. But then comes the final crucial step, selection, where it has to pick the best fix from all the ones it generated. And what's its final score? 57.4%. So let's break down each of these stages. First up, context. A modern codebase can have millions of lines of code. So how on earth do you find the handful of relevant files? Well, on the left, this graph shows that by giving the AI a context window of about 128,000 tokens, which are just pieces of words or code, it can find all the necessary files 92.6% of the time. And the chart on the right shows the compression factor. On average, the system shrinks the amount of code the AI has to sift through by over 50 times. It is an incredibly efficient way to find that needle in the haystack. Now we get to the generation stage, and this diagram illustrates it beautifully. It's a two-part process using what the paper calls state machines. Just think of them as a structured playbook for the AI to follow. First, you've got the testing state machine on the left. Here, the AI's only job is to write a test that can successfully reproduce the bug. It runs the test, gets feedback, tries again, until that test works perfectly. Only then does it move to the editing state machine in the middle. Here, it takes that working test and the code-base context and starts writing an actual code patch. It applies the patch, runs the test, gets feedback, and refines the code again and again. So, just to recap this whole generation loop. Step 1, an AI agent writes a test to prove the bug is real. Step 2, another agent uses that test to write and rewrite a code fix until it passes. And here's the really important part, Step 3. They run this entire two-step dance 10 times in parallel. This gives them a rich, diverse pool of 10 different possible solutions for every single bug they tackle. So, that's the theory, right? An intelligent system for finding context and then generating a whole bunch of possible solutions. But how well does this whole thing actually work on the super tough SWE bench? Let's look at the results. Okay, this number is kind of staggering, 69.8%. This is what they call the coverage score. What it means is that for almost 70% of the tough problems in the benchmark, at least one of those 10 parallel attempts created a perfect working fix. This is the system's theoretical maximum performance, if it could somehow always pick the correct solution.
But of course, it can't always pick the right one. The final real-world score is 57.4%. This is the percentage of bugs it actually managed to solve after running its selection process. And that gap between almost 70% and 57%, it highlights a new critical challenge. Generating solutions is getting easier, but selecting the right one, that's hard.
And this brings us right back to that idea of compute. This graph shows the trade-off between those two strategies. On the vertical axis, you've got performance, and on the horizontal is the amount of compute, or, thinking time that was used. Each colored line is a different number of parallel attempts, from 1 to 10, and the dots along each line represent more serial iterations for each attempt. What's so fascinating is that after the first few iterations, the lines all start to flatten out and bunch up together. This basically means that spending your budget on more parallel attempts versus more serial thinking time starts to give you similar and diminishing returns. It's a really interesting balancing act. The paper itself really hits the nail on the head. That performance gap, the one between what's possible and what the system actually achieved, it's all about one thing: selection. I mean, having the right answers somewhere in a pile of 10 options is totally useless if you can't figure out which one it is. So, how do you pick the winner? This chart lays out their methods. Just picking one at random would get you about 46%. Using the tests they already generated to vote is a bit better at 53%. But their best method, the selection state machine, is what gets them to that final score of 57.4%. This is another AI agent whose only job is to look at the top 3 candidates, write brand new tests specifically to tell them apart, and then make the final call. It actually recovers about half of the performance gap between just guessing and having a perfect oracle. Now, to really prove how good their selection method is, they ran one final experiment, and they called it Barrel of Monkeys. The idea was simple. What if we use our selection method not just on our own solutions, but on a big mix of solutions from all the top AI agents on the leaderboard? And wow, the results are incredible. Just look at this table. The best single agent in that whole group scored 62.8%. But when the CodeMonkeys selection method chose from the combined pool of everyone's candidates, it hit a score of 66.2%, outperforming every single individual system. And even more amazing, the potential coverage of this combined pool was a massive 80.8%, which just shows how many of these problems are now solvable if we can just crack this selection problem. So what does this all really mean for the future of AI in software development? Let's wrap this up with the key takeaways and a look at what's next. The researchers are really upfront about the limitations. The context retrieval isn't perfect yet. The generation process can sometimes spit out 10 solutions that are all basically the same. But the biggest area for future work by far is selection. Closing that 12-point gap between the potential score and the actual score, that's the holy grail right now. So if there's one thing to take away, it's this. We've gotten incredibly good at getting AI to generate correct code. That part of the problem feels like it's on its way to being solved. The next great challenge, the one that this CodeMonkeys paper highlights so brilliantly, is teaching the AI the wisdom to know which solution is actually the right one. Hey, if you enjoyed this deep dive into AI research, and you want more explainers that break down complex papers just like this one, make sure you subscribe to VibeDoc right here on YouTube. Thanks for watching.